So today we have the privilege of having Dr. Muneeb Ahmed. He's a PGY3 in the GIM program at University of Toronto. I happen to have the privilege of working with him in the last number of years, and he's been very productive, and we work on a number of different projects, which you'll hear more about, especially on artificial intelligence and in the field of cardiology. He's also very keen on joining us as being a cardiologist, so he'll be applying through comms. So wish him good luck, and we'll try to help him. Without further ado, I'm going to pass this on to him and about Information Revolution 3.0. Let's learn what is that and how we can use AI in cardiology and day-to-day practice. Please go ahead.
Good afternoon, everyone. Thank you, Dr. Chow, for the introduction. My name is Muneeb. I'm one of the medicine residents at UFT. Thank you for joining Cardiology Grand Rounds. Today, we will explore Information Revolution 3.0 and what artificial intelligence means for everyday cardiology practice. My goal is to give you a clear mental framework, show you real-life examples that work, and leave you with some practical tools to judge any new AI products that come across your inbox. The three learning objectives are: one, summarize the three phases of the information revolution and place current AI tools within this framework. Second, describe at least three practical AI use cases already improving cardiology practice, including echo, ECG, and administrative workflows. And then finally, evaluating the current evidence base for cardiology AI tools with emphasis on performance metrics, external validation, and real-world readiness. First, let us ground ourselves in history. Humanity has gone through three seismic shifts. The first was the agricultural revolution about 10,000 years ago, which gave us farming, surplus food, and the first cities. The Industrial Revolution in the 18 and 1900s replaced human muscle with machines powered by steam and electricity. The Information Revolution, which first began in the 1970s, digitized information, paired it with these things called computers, and connected the planet through networks. Each revolution multiplied productivity and changed the way we live. We can slice the Information Revolution into three phases. Phase one was personal computing, when desktops and early mobile phones let us store and process our own data. Phase two was the internet, which made almost any piece of information available anywhere on Earth. Phase three is artificial intelligence, which is the basis of this talk. Here, models learn patterns from massive data sets, generate new text, images, or predictions, and it's the stage where we're going from passive storage to active reasoning. To make this concrete, this is just a demonstration. I asked ChatGPT to summarize the 2023 ACC guidelines on ACS. Please watch three things. We'll just wait for it to load one more time. One is how fast the model responded. Two, look at how it organized the information into very clear sections. And then finally, look that it doesn't actually give citations at all unless we actually ask it to. This sets up both the promise and the problem of generative AI. Cardiology has always been an early adopter of technology. This timeline shows that journey. We begin with rule-based ECG coding in the 1960s, moved to consumer atrial fibrillation detection on smartphones in 2019, and then we, at this point, have gone into deep learning echocardiography in 2020 and 2023. Each milestone is built on better data and better algorithms. Early rule-based ECG coding began with the Minnesota Code in 1960, which sets the standard for computer-readable ECG findings. Researchers punched binary versions of ECGs into an IBM mainframe and applied handwritten rules to label Q waves and ST changes. This project proved that if we can encode physiology into data, we can potentially automate interpretation. Fast forward a couple of years, in 2019, the FDA cleared Cardia Mobile, which is a 6-lead personal ECG. This is a step toward home rhythm assessment. This project looking at EchoNet dynamic matched or even beat sonographer performance on EF estimation, and it was actually steadier on repeat scans. A 2023 RCT that looked at this particular program showed that the initial EF assessment by AI was non-inferior to sonographer assessment, and that cardiologists actually trusted the AI interpretation more than the sonographer interpretation. 3 lessons emerge from these milestones. First, performance follows data quality, not interest. Secondly, external validation is mandatory because hospital populations are extremely different, even within the same city like Toronto. Thirdly, adoption only happens when the tool fits the workflow and solves a particular pain point that clinicians feel. These lessons apply to all sort of AI models and particularly generative models, which we'll talk about now. Generative AI, the main concept behind this is transformers. Transformers change how models handle language. Instead of hand-engineered rules, they learn patterns from a large amount of text as well as code. At a cardiology scale, this meant, absorbing all the guidelines, all the policies, and all the different patient instructions available on the internet into one answer. I'll explain how this works in plain terms so we can judge the benefits and the risks. Traditional code is deterministic. You have one input and then you have one output. The difference is large language models are probabilistic. They predict the next word based on learned patterns. It's not always the same output. The model chooses among likely words using a process called sampling. Small changes in the random text can change the answer. This is why when you put the same prompt into an AI, for example, ChatGPT or DeepSeek, it can actually yield different outcomes despite the exact same prompt. The key mechanism to this is self-attention. Each word looks at other words in the sentence to decide which matters. Our team thought that it would be helpful for clinicians to have a simple map for safe use of AI, which is why we wrote a primer for cardiovascular care. This primer gives a mental model and a checklist for practice in cardiology. 2 points in this primer matter today, which is tokenization and token prediction, because they explain both strong summaries as well as common errors we see in AI. I'll use this model to explain when summaries succeed and when they fail. The next slide is going to talk about the full pipeline from data to answers, which goes through large language models in detail. Here's the pipeline from end to end. First, a crawler collects texts from websites, books, and codes that are licensed on the internet or permissibly scraped. Secondly, we clean the text. We remove low-quality pages, and we split the text into small chunks. Each chunk is converted into a vector, and these vectors are processed by NVIDIA chips and Intel chips, which is why there's been sort of a craze along those companies. A vector is a list of numbers that captures meaning. Fourth, we store these vectors in a database that can search by meaning of that word. So when it comes to question time, as an end user such as us putting in a question, the system finds the most similar chunks of information, passes them with the question to the model, and asks for a draft. If the user, for example, yourself, asks a follow-up question, the system retrieves new chunks of information that was in the vector database and then passes them into the system itself and then refines the draft that it already made for you. This is why when you give multiple prompts to ChatGPT, the results improve with iteration. The system keeps pulling better content and context because it understands better what you are asking for. There's 2 important limits within this. First, if you can imagine, if the source contains errors, for example, the data they pulled in has errors, the model will repeat the errors. Secondly, if there's no relevant chunks of information at all to retrieve, The model may artificially fill gaps with something that reads really well, but is completely wrong and inaccurate. This is important to know and keep this in mind when we talk about privacy and patient health information. What you paste in and where it goes really matters. We made another figure in our paper where we talked about how this can help in cardiovascular care. This really wonderful diagram was made by Alyssa, who is the administrative staff for Dr. Chow here at St. Mike's Hospital, and we'll go through all of these in great detail. Over time, the amount of parameters in GPT models has really exploded, as you can see on this graph here. GPT-2 had about 1.5 billion parameters, which essentially just reflects a lot of data. GPT-3 had 175 billion, so exponentially more. And GPT-4 is thought to have a trillion, capturing more complex patterns within the data, but also requiring significantly more computing power. All of these models were trained on large collections of public text, so they embed a broad slice of the human knowledge as a collective. The size of the information does help, but alignment and data quality matters more for clinical use. With the scale of ChatGPT and other models, they've become more fluent, but unfortunately, the risk of confident errors also goes up. To counteract this, the developers use something called reinforcement learning from human feedback, which aligns answers produced by the models with human preferences, i.e., is this answer helpful or harmful, as well as safety rules made by the developers on the back end. Instruction tuning plus human feedback is central to these current models. Now that we have a simple model of how these work and how they grow, we can take a look at general strengths and gaps. Strengths, rapid summarization and drafting. It has a really wide knowledge across multiple domains. It produces extremely organized and structural output when prompted. The gaps are it does hallucinate facts and citations. There are bias and equity concerns, which we'll talk about. It also may adversely affect reasoning during training, which we'll talk about as well. One of the most clinically important problems with AI is hallucinations. These occur because hallucinations don't learn the truth, they learn patterns. The training text includes both accurate and inaccurate claims. For instance, it can include many papers that refute the opinion that vaccines can cause autism, but it also includes the paper that did the thoroughly debunked paper that did find a non-existent link between vaccine and autism. The problem is if the models are not connected to trusted sources, the model produces fluent, very coherent appearing falsehoods. We can reduce the risk by retrieving guidelines, by using checklists, and by requiring expert review, but we can't eliminate the risk, and we'll talk about this going forward. This also explains why some of these answers can be out of date, and we'll cover that in the next slide. Base models, for example, ChatGPT-4, learn from a past snapshot. They don't know what's going on today unless we add a browsing link or a local newspaper article that can update its information. Some versions, like the newer ones like ChatGPT-5, can browse or use retrieval to read current documents. That browsing reads a page, answers the question, and forgets. It doesn't actually change the model's memory because the model isn't being trained on today's data. One simple example of hallucination is right here. This is a completely non-existent link between Pompe disease and liver involvement, but it creates a really well-organized and coherent appearing link that just does not exist. The other problem is AI can save time, but over-reliance can hurt reasoning. There's a recent MIT study that was published on a preprint website, not peer-reviewed currently, but it saw that students who relied on ChatGPT, and this is mainly college students, showed less brain engagement and produced poorer essays compared with those who used Google or no tools at all. Participants can become lazier, often just copy pasting AI output, and an excessive use of generative AI can erode critical thinking skills, especially in learners, and that includes residents, fellows, and so forth. What can large language models do for clinicians today? Currently in family medicine clinic, they're used to generate multiple family medicine clinic here at St. Mike's Hospital. They're used to generate multiple choice questions, summarize lengthy clinic notes, draft patient letters, translate instructions, and even outline discharge summaries downstairs. All of these are low-hanging fruit because the risk of clinical harm is small when a human evaluates every part of that text. I'll now provide 5 concrete cases of where AI can be useful to cardiologists. We'll start with patient education, where benefit is clear and the risk is quite low when a clinician looks over all the text. Looking at a couple of studies that evaluated AFib and patient education, evidence was overall fairly mixed. There was a study in Curious that showed ChatGPT answered about 86% of questions correctly. 98% were at least partially correct as per the study. There was another study looking at ChatGPT Plus, which showed an even lower percentage of correct answers, about 84%. The problem in both of these studies is that they very rarely produced any references at all. So ultimately, we need to keep a very critical lens, and we would not recommend patients ever using any sort of AI at this current time to ask questions unless it's very heavily supervised. We're going to now play a short video on patient education for heart failure.
Living with heart failure can sound daunting, but it doesn't have to mean giving up the things you love. Heart failure means your heart isn't pumping blood as well as it should, either because it's too weak or too stiff. In everyday life, this can show up in a few ways. You may notice you're more tired than usual or get short of breath doing simple activities. Swelling in your ankles and feet is another common sign. Sometimes you might wake up at night coughing or feeling like you can't catch your breath. All of these are signs that your heart may need extra support. One of the most important things you can do is check your weight every morning right after using the bathroom. If you notice a sudden increase, like 2 kilos in 2 days, it could mean you're retaining fluid, which is a warning sign. Managing heart failure is a team effort between you, your family, and your healthcare providers. Take your medications as prescribed. These may include ARNI, ACE inhibitors, beta blockers, MRAs, SGLT2 inhibitors, and sometimes a diuretic to help remove extra fluid. Each medication plays a specific role in helping your heart work better and slowing the progression of the disease. Lifestyle changes are just as important. Keep your salt intake under 2 grams a day. Limit your fluids to about 2 liters per day, unless your doctor gives you different instructions. Stay as active as you can within your limits. Eat plenty of fruits and vegetables and avoid smoking. These simple choices can make a big difference for your heart health. If you notice more swelling, trouble breathing, or a cough that won't go away, contact your clinic right away. With the right habits and support, you can continue to live a full and active life, even with heart failure. And remember, always talk to your own doctor for advice that's tailored to your needs.
This entire video, not just the script, the entire video was completely generated by AI. The people in the video are AI generated. All we did here was ask ChatGPT to please create a script for a patient education video on heart failure. Dr. Chow and I then reviewed the script, and then we put it into an AI video tool. The cost of this entire project was 0. We use no patient data. The narration is clear. Captions are accurate. This helps patients and caregivers return to key points at home. We're currently running a study at the Toronto Heart Centre to measure how patients felt subjectively after viewing. We're looking at confidence, understanding, and we're actually testing the patients to see if their knowledge improved after watching the video. Early feedback is very positive, but we're not subject to peer review yet, so the jury is still out. Now, education for trainees. Our research group asked a very simple question. Can AI help build cardiology exam style questions without lowering quality? Read both questions, the question on the left and the question on the right. One question was generated by an AI after it looked at a St. Mike's echo video about hypertrophic cardiomyopathy. The other question was written by Dr. Chow and Dr. Flora Huang, one of the echo fellows 2 years ago. I would like the group to think just in their head which question you think is AI. The question on the left or the question on the right. I'll give it about 20 seconds. If you did not get it right, do not worry. In our study, recognition was about 50%. We're exploring a collaboration with the Royal College to see if a large language model can support question generation under faculty reviews. Performance was the same by the fellows on questions that were made by AI, as well as the questions made by faculty, about 75-ish percent. Fellows could not identify whether the questions were made by humans or AI better than chance, about 50%. Ultimately, faculty review remains central, and we can use AI to expand the bank of questions, but experts need to curate what we keep. And this is what we're doing in our collaboration with the Royal College. Another case is large-scale ECG interpretation. A deep neural network trained on about 900,000 ECGs and achieved really high scores on rhythm, access, and ACS, compared to the traditional machine learning ECG interpretation that we see on top of the ECGs we read. It was better in 13 of 20 patterns, and it was non-inferior in all the rest. So ultimately, high accuracy across diagnoses, better than the rule-based interpreter we have now. But again, central to this, all of this, is a cardiologist reading the ECG for interpretation. Case 4 is reducing administrative burden. A practical win is documentation. The workflow is simple and it is being used at the family medicine clinic at St. Mike's. The clinician prompts the system with a short summary. The model drafts a note or a letter, like a sick note. The clinician edits and signs. Time saved can be reallocated to patients. And again, human review remains central. This is another live prompt. I simply asked the model to create a discharge summary for an uncomplicated anterior STEMI who received 1 stent to the LAD and no LV thrombus, recovering well. This is what we get. Note again the very structured sections. Look at the medication list. And look at the very clear follow-up plan. It's important to note that it left the drug doses for the medications blank because it knows that's an area where it can struggle. So they left it for the physician to put in. One of the problems that AI has is with equity. We had a 2024 Lancet study that found a very large demographic skew in vignettes generated by GPT-4. And it actually changes diagnostic ranking and management with race and gender. This supports that any sort of deployment of these models needs to have formal bias testing in any sort of deployment. Under the Ontario Personal Health Information Protection Act, you are not allowed to paste any patient information into public ChatGPT, and that this counts as unauthorized disclosure. Unity Health policy is also clear. No patient identifiers in any public generative AI tool. To assess AI tools in this context, we need to ask 5 questions. The first question is purpose. What problem are we planning on solving with this AI? For example, reducing note writing time by 30% with no new errors. The second point is inputs and outputs. What data goes in and what data comes out? For example, even file types, like are we putting in a PDF or are we putting in a Excel file or just text? Thirdly, performance. What is our gold standard or our reference standard that we're comparing this AI model to? And what's our safety margin? For example, it has to be non-inferior within 5% on accuracy within a two-sided 95% confidence interval. Fourth, human factors. Where can it fail? What is our fallback? What is the rollback plan if there's an update that breaks the workflow? And then finally, and most importantly, is security and privacy. Does the vendor that we're using keep the data within our center or within Canada or another approved region? Do they meet the standards both from the government and from the hospital policy? We can only move ahead when these are very clear and written down in a contract. These contracts must protect patients and staff. Data has to stay in Canada. The vendor cannot use clinical data to train models. We always need to complete a privacy assessment and a threat assessment. With these contracts defined, we can prepare teams with clinical use. This is a framework that we built for this group. Low risk sort of systems would be drafting sick letters, prior authorization, back to work notes, and public education scripts. These are safe because a clinician reviews all of them in detail and no one makes a diagnosis. More of a medium risk approach would be drafting daily notes for clinician editing. This can save time, but again, this is on the patient health record, so clinicians must review every word. The more high risk category includes asking AI for diagnoses or treatment suggestions. This is something we should all avoid until there is very strong local evidence, approvals, and close monitoring. The whole point is AI has to start low risk, measure, reassess, and then keep going with low risk for now. This is an education use case that fits our low risk tier. If you teach, AI can generate fresh exam questions and OSCE stems in seconds. Once again, faculty review is needed before adding them to your program question bank. Why AI matters to cardiology and allied health professionals. Ultimately, this plan in its current form does fit Unity policy. There's no patient identifiers in any public tool. We improve teaching today with non-patient examples in talks. We build exam banks with faculty review. We cannot use it clinically unless we go through an adoption process into routine clinical use that we'll talk about shortly. A systematic pathway to bringing AI into a clinical setting is as follows. Number one, you need to pick a single use case with clear benefit. Two is complete privacy and threat risk assessment, sign a contract, and three, run a short pilot with human oversight and a stop rule, and then finally monitor time saved and errors, then decide to continue or stop. You may be asking, Muneeb, this is all interesting, but this seems quite onerous and time consuming. Is it even realistic in clinical world, much less the cardiology world? Has this even occurred in Toronto before? My answer to this is yes, it has. Right here at St. Mike's Hospital on the medicine floor, we have an amazing example of how this process of adoption of AI into routine clinical use works in the form of ChartWatch. ChartWatch is the GIM early warning model. Everybody here who has rotated or on internal medicine at St. Mike's Hospital while we were on Sorian can remember the big warning notifications on the team phone that warned us of impending patient deterioration. The warning that you can see on this picture here is made by using machine learning to analyze around 13 variables that includes data in the vitals, lab work such as hemoglobin, white count, platelets, and even recent antibiotic start, and puts them all in a model that continuously evaluates the patient and produces a warning if needed. The evidence that Dr. Verma published speaks for itself. There was a 26% reduction in unanticipated mortality on the GIM ward with this deployed. Currently, the St. Mike's data scientist team are integrating this model into Epic in silent mode first, so they can check the accuracy and workflow burden without any alerts firing. Once performance is acceptable, they plan to turn this on to clinicians around November of this year. What's exciting for our research group is that we're working with the ChartWatch team to retrain the model onto different variables and bring the system to cardiology. The plan is hopefully to start with the ward service sometime next year and then to consider ambulatory use. Data stay within approved systems. Every alert has a clear owner and an audit trail. Success means fewer missed deteriorations, faster response, no alert fatigue. The hope is to track lead time over usual care, alerts, clinician response time, transfer from the ward to the CCU, transfers to a different site for advanced therapy, and any RT calls. If any metric worsens, we pause, we readjust. Other future models include federated learning, which lets hospitals train a shared model without sharing raw patient records. Here's the flow in plain steps. 1, each hospital keeps its own data inside its own firewall. 2, a copy of the model goes to each site. 3, each site trains the model only on its own data. 4, each site sends only the updates of the model to the server and not the patient records at all. 5, the server combines all of the updates and sends back an improved model to all the hospitals. We repeat these rounds continuously. No raw clinical data leaves any hospital at all. You would ask, why is this helpful? This basically eliminates all data movement. You have better privacy. There's a wide mix of patients and sites differ. We all know how different patients are at Sunnybrook compared to UHN, compared to St. Mike's. Ultimately, we still need contracts, audit logs, version control, local validation before using any of these. One of the local examples I can think of is maybe St. Mike's and UHN could train together this way. So both centers learn together while each clinician, each hospital's clinical data stays local. Another area of improvement where we're working on is patient devices and summaries. You have home devices like Apple Watch and Cardia that can capture rhythm and activity. You can essentially have faster triage and clearer instructions. For now, we can only test with synthetic cases and keep use outside clinic, but I'm sure in the near future we'll be incorporating these things into our clinical world. This is a very new concept talking about digital twin. A digital twin is essentially a patient-specific electronic heart model. We build it from lab work, CT, echo, ECG. And what it essentially does, for example, for valves, it can test sizes and positions for TAVI before the day of the case. For rhythm care, it can simulate ablation lines and predict which areas are less or are likely to trigger arrhythmia. Again, this is all early studies. It shows some promise for planning, but there's no broad clinical trial data yet. What matters to us is whether twins or digital twins can actually improve patient decisions and outcomes and not just simulation. We'll ultimately have to watch for studies in this area that report patient outcomes and real-world impact. There's 3 priorities for our center. One is evaluating large language models on local data with pre-registered metrics. The hope is to build open and transparent benchmarks for any cardiology tasks. And finally, we need to study long-term effects on clinician learning, patient understanding, and outcomes. And ultimately, we need to publish both successes and failures so others can learn. The sort of standard 10-year predictions from a healthcare perspective are: 1, models will eventually probably sit around inside the EMR for summarization and triage. This is already starting to happen, with Epic expected to announce an AI scribe that will be available throughout the world in the next few months, including Canada. The other prediction is hospitals will likely form a consortia to train models with federated learning. Finally, clinician decisions will be a human responsibility. I don't anticipate AI ever making a final call, but certainly I think in the future it may help with the first draft. 5 summary points for Monday afternoon. Number 1, transform documentation. Ultimately, AI can be used for drafts of patient education or question banks, but not for decisions. Second, triage tasks, automate administrative work to free clinician time. 3, teach responsibly, use non-patient examples with heavy faculty oversight. 4, translate with care, ensure privacy and fairness before any adoption. And then finally, trust but verify. Validate any output against evidence every single time you use AI. Just ending on this quote that Dr. Chow recommended: like it or not, we live in interesting times. There are times of danger and uncertainty, but they're also more open to the creative energy than any other time in history. I'd like to thank Dr. Chow and the co-authors for their mentorship and support. Thank you for listening. I'm happy to take questions.
Thank you, everyone, for joining. Thank you, Muneeb, for presenting another review of the AI in cardiology. Last week, Dr. Hamza actually did that, but it's different approach. So he was talking about other aspects of AI in cardiology, especially in clinical trials and much in other data sets. And the way you took it, it's slightly different. So it talks more about the basics and how we can use it and better understanding. So let's have questions. So this is a very exciting area that everybody's into, and so I mean, maybe I'll just ask one question and see how you respond to this. So ethics is always a major problem for us, and how do you actually deal with all the ethical issues and also privacy issues? You alluded to it in part of your presentation.
I think collaboration with government as well as hospital leadership on creating guidelines, how to use it appropriately and protecting patient information. This is an area of consistent development, and I think there needs to be a concerted effort among leadership to talk about safely using AI in any context. And I think this is something that has to be decided from a government level first.
Well, I think it has to be top down because it's one of those situations where we're facing now. Way back when we had started to have computers on the floor, and I remember I started doing clinical medicine with no computers anywhere to be found, or even a personal digital device or assistant. So all these things came afterwards. All we had was perhaps a mainframe to look up lab results. That was it. And then the computer is everywhere. Then there's issues of privacy on the computer, and then it becomes the internet era where everything is being Googleable, and then patients start Googling everything, and then comes to us. And then there's also issues of sharing information on the internet. Now we have AI. So I think, that's where the 3.0 comes from. So Sammy has a question. So please go ahead, Sammy.
Okay, thanks, Muneeb, for the great presentation. And congratulations on the work and publication. So it's more of a comment actually, because you shared CT or AI powered CT analysis of Valve and TAVI, and I have to say it's not far from being used in clinically. There are many companies. Actually had a meeting this morning with a company that does you upload the study, obviously with the patient consent, and it does as complex of analysis as tricuspid and mitral, which is usually more complex than even aortic from a measurement and from anatomy point of view. And actually many companies uses such surface. I mean, obviously it gives the option of doing manual assessment, but it's been really reproducible measurements in patients actually we treated clinically using such software. So I think it's a reality, and as you mentioned, it's the potential is huge.
Yeah. So maybe I'll add one more comment, which is often how I end the presentation about AI is people often ask whether AI can replace physicians, but my opinion is physicians who use AI will replace physicians who do not use AI. So that's the way I see it. So Bob has a question. Go ahead, Dr. Howard.
Yeah, thanks, Chimeng and Muneeb. Great presentation. So massive amounts of data. I'm wondering about cost. I mean, there's got to be cost here. Who pays? How are we gonna afford all this?
Dr. Howard, I think that's a great question, and I think comes back to the point where each GPT model uses even more parameters, even more data. The computing costs of these go up exponentially. Initially, OpenAI, the creators of ChatGPT, was sort of a small startup that a few people could use, and now it needs investments, and it's running at a loss, by the way, but it gets routinely billions of dollars of investment and running still at a loss, just because the pure amount of processing power you need is actually affecting the electricity grid within America right now. It's affecting the water grid in America right now as well. And these things will continue to get worse until we make AI more efficient. And as we get, broader access to AI across the world, it will ultimately cause extremely high energy costs. And I think this is an area of development where we need to make more efficient chips and deploy AI more sustainably.
In the meantime, you can get your feet wet, so as to say, by paying $25 for the customized model or the higher version of like ChatGPT 5 to just got released last week. Alternatively, you can use a free version just to try it. And they're actually very interesting to try. All I can tell you. So yes, cost is going to be a huge problem. Energy consumption is a huge problem. You probably heard from the news that nuclear plants is actually being revived, including the 3 Mile Island one in the States that Microsoft is actually looking into reviving to actually provide all the energy supply. And if you ever invest or look into the investment world, U.S. energy at some point within the last couple of years has actually increased in stock price, same as all the semiconductors, which is now in the top of the news every day.
So maybe just a follow-up in that regard, ChartWatch, which was running for a while and now is obviously has to migrate from Saurian to Epic. Is there a sense for what that costs? I mean, who's paying for that and kind of how is that coming out of grant money, and just a sense for what ChartWatch costs?
That's a great question, Dr. Howard, and one that Dr. Chow and I were kind of smiling about this because we know the background behind this. Unfortunately, one of the main limitations of ChartWatch was there's a lot of funding associated with paying data scientists, all the data, anonymizing it, keeping it private. It was initially run on grant money that Dr. Verma had won from CIHR and in his role as the AI chair. And the reworking of the data of the ChartWatch for Epic needed another grant from CIHR as well as some other private grants. Currently, with our hope of translating this into cardiology, we're hoping to get another grant for that purpose because, as you mentioned, like a lot of this cost is computing costs and paying for data scientists and such. Dr. Shao, you may have more information about this as well.
Well, actually, we don't know how much it is, but both Muneeb and I are very keen on looking at using ChartWatch, introduce it into the cardiology world, and we're looking at how much it would cost to actually do the customization for our cardiology patient as opposed to be just GIM patients. And there is a cost involved in it right now. I mean, there are commercial applications potential. So like everything else, there's lots and lots of small startup company that are looking to commercialize it. As I always mention in my AI presentation, we have tons and tons of papers that are out there in terms of the feasibility of using AI in various different aspects of our cardiology world, both clinically, echo, nuclear, cath, et cetera, is to no end actually, and arrhythmias. But the real application out there is far few in between still. So many companies are still running at a loss, like the original internet boom. So I mean, it still have yet to see. And I mean, a good example is there's a echo company that we're working with, looking at doing all the measurements using artificial intelligence. After you upload it, it will turn back a number, but you know, it's fairly expensive. And within our budget environment, we actually cannot afford it unless you have a huge grant or something. So you're absolutely right, Bob.
So, and the other thing is that is the updating of the AI model. So my understanding is that, you know, when ChatGPT came out, they sort of cut off the data was up to a certain, and then they just didn't add anything new for several years. So it didn't include sort of new stuff, right? So how are these models we're looking to use? Will they be continuously updated so they're absolutely up to date with everything that's happening, or is it sort of, do they cut them off at some point and then, you know, a few years later maybe update them? How do you manage that?
So I think it depends on the model itself. As you mentioned, like GPT-3 and GPT-4 was sort of locked at January 31st, 2019, I think is my understanding. And my understanding was that if you provided it with, for example, a newspaper article about what's happening today, it would sort of read it and answer it based on the information you provided. But the newer version, like GPT-5, actively can browse the internet on your behest. So it can read current documents from today. So it can incorporate that today data into its own model and actually train on it. So that's the difference. It can train on today's information if you ask it to. In the past, GPT-2 or 3 did not have the computing power to do that, and it was fixed at January 2019.
Yeah, it becomes more hybrid. The real large language model, you have to actually have a cutoff date where you can no longer train after that because you need to close the database. But nowadays, the new one actually knows that if you need something contemporary, they will go out to the internet to actually acquire that information. So in many ways, it's a hybrid. So you know, Google was actually banging on the fact that OpenAI will only look at a certain date, then they still have all the contemporary or the current search business. But now, you know, all of them have to do the same thing and look at this hybrid model.
But do you have to pay for those? Like is ChatGPT 5, you have to pay a monthly fee?
I think it's free right now.
Yeah, there's a free version and there's a premium version. The premium version is adding about $25 US per month. To me, is one of the best $25 I spend a month because you know I use it quite extensively to improve my work efficiency, and so you know it's something worth, like for some people when you use it a lot, it's really worth investing. I use it for improving my English communication, even editing medical journal like submissions, and also help interpret echocardiography to try to allow me to make less mistakes, and things like that. So if you use it wisely, like everything else, it can save you time and actually turn that time back into reward for paying the money that you spend in using these tools.
So I'm monopolizing the questions here, sorry, but why is it better? Like if you pay money, you get something better. Does that mean the free model is actually making mistakes and the pay model actually makes fewer errors? I mean, what's better? What's better about the one you have to pay monthly for versus the one you don't?
Yeah, the free model, my understanding is the free model actually has a smaller trained data set and also slower, and they dedicated less CPU time or GPU time in this case for your request. But if you pay for it, then you become like a special VIP member, so as to say, and then your response will be faster, more detailed, and more accurate. So people have actually done studies on this. And I mean, one of the one that I can quote is people actually look at all the different free models versus pay model. And in terms of answering cardiology questions, and definitely the one that you pay actually answer questions much better. Great. Well, thank you, Bob. Thank you, Muneeb, for your presentation. I think we can let everyone back for another 5 minutes of the time. And may we all live in very interesting time because